I am Varun Joshi and welcome to day one of our Jenkins Basics to Production course. In this very first lecture, we are setting the stage by covering the fundamentals every DevOps and SRE engineer must know before touching Jenkins. And here is the agenda for today's lecture. Firstly, we will discuss the phases of software development life cycle SDLC, how modern software moves from idea to production. Next, we will discuss waterfall and the agile DevOps model, why we shifted from big bang releases to continuous delivery. Then we'll move on to compiled versus interpreted languages. What happens to your code before it runs? Next, we will discuss the key building blocks, which are artifacts, runtime, and dependencies. And finally, the build process, which is of extreme importance for us DevOps engineers, both for containerized and non-containerized workloads, so you understand how applications actually get prepared for production. By the end of this session, you will have a production level understanding how software is built and deployed, which will make everything we do with Jenkins later far more clearer. So let's get started. Phases of SDLC. Firstly, SDLC is software development life cycle, and this is what we will use. What you see on screen is what we use in Agile and DevOps model, which is the latest and the greatest one. So now I want you to understand that there are millions of applications that are around the globe. Are all the applications adhering to this SDLC framework? No, it is not that. But whether an application adheres to all these phases depends on the maturity of the application. So if I talk about an enterprise grade application like amazon.com or netflix.com, they would definitely be adhering to the SDLC process. Now, SDLC at large is not a tool. It is not something that you can purchase. It's an ideology that you must have in your application if you want your application to have the latest and greatest modern design. Hence, SDLC is a logical framework which defines how you should be developing your application. And in this lecture, we will start by discussing the different phases in SDLC. Now, like I said, SDLC is not a tool, it is a framework. But within the phases of SDLC, you will of course be using different tooling. For example, if I talk about the first phase, this is requirement gathering. What would requirement gathering? What are the tools that I would use in requirement gathering? I would be using Microsoft Teams, Zoom, or WebEx for meetings. I could be using Excel or Microsoft Office in general to prepare my documentation. I could also be using tools that I would use to create my diagrams, for example, diagrams.net or eraser.io, etc., etc. So what I'm trying to tell you is, in each of these phases, you will be leveraging different tools, but SDLC at a very high level is just a framework. Now let's discuss the first point. Requirement gathering. What happens here? As the name implies, this is the place where you gather everything you can about the application. Now, when I talk about an application, there are two things that we talk about. First is functional and second is non-functional. Now, what are functional requirements? Functional requirements are what the system should do. For example, if we are developing a banking application, then it should be able to show users their account balance, their passbook. They should be able to check if they can apply for a loan, if they are eligible for a loan. They should be able to calculate interest rates and so on. That is the functional requirement from a banking application, that this should be able to do these things. Then what are non-functional requirements? Now, non-functional requirements are anything that are not directly application. For example, what should be the infrastructure on which this application must be deployed, whether we have to adhere to any compliance standards or not, what will be the RTO and RPO for my application, what will be the DR strategy for my application, what will be the availability requirements for my application. These are non-functional. So functional are essentially anything that your developers will be coding for the application to work properly, and non-functional are anything that will be supporting your application. For example, the underlying hardware will be helping my application to run. So underlying hardware is a non-functional requirement. I hope functional and non-functional is clear to you. Then third point is compliance and security standards. Now, at this point of time, I want to differentiate between security and compliance. Security is a subjective term. For organization A, security implies not allowing port 22 to the outside world, not allowed at all. For organization B, security could mean allowing port 22 but only from a specific public IP. Both of these are security requirements and these are subjective. So security in general is subjective. For one organization or for one application, something could be secure, and for another, something could not be secure. But when I talk about compliance, compliance is dealt with different compliance standards. So if I say my application is compliant to GDPR, then my application must meet the requirements that are laid out in GDPR. Now, GDPR is a popular compliance standard when I talk about Europe. So in the requirement gathering section itself, you decide what all are the compliance standards that your application must adhere to. Now, these compliance standards could be PCI, DSS, GDPR, ISO 27001, even HIPAA. If you are doing insurance within your banking application, then you must also adhere to HIPAA. So in the requirement gathering phase, I am just saying that these are the compliance standards I must adhere to. I am not defining how we will adhere to them. I am just saying we must be adhering to compliance standards. Similarly, we must have a DR. Now, how that DR is achieved, we don't know yet. We want high availability, but how that high availability will be achieved, we don't know that. All those things will be done in the design phase, which we will discuss next. Now, before I move to design, let's also see plan for reliability and environments. Now, in the requirement gathering phase itself, we decide how many environments do we need. Do we need just dev, staging and prod, or do we also need a QA or a testing environment as well? So all these things are decided in the requirement gathering phase. Now, once all these things are collected, your program manager would be the person who would be overseeing everything and will be working with different project managers that are part of that project. And then you folks, your DevOps architects, your application architects, your developers will be participating in these meetings, and you will have documents that will have all the requirements. Then there is the design phase. Now, design phase is architecture and API contracts. Here is where you define how you will achieve whatever was defined in the requirement gathering phase. Now, I want you to clearly know that these phases are for both developers and DevOps. It is not just the DevOps team who will be participating in all these phases, because we are talking about taking an idea to a running software. So when I talk about creating an application, it is not just DevOps, you will also have developers here. So design is essentially how the system should function and interact. Second point is testability and observability built in. Now in this phase itself, you will design for everything. So be it your observability posture, security posture, testing posture, high availability, DR, here you will be defining how you will achieve whatever was gathered in the requirement gathering phase. So security and branching policies. Now you know that whenever we talk about developing a software, you know that the entire code is contained in some sort of source control like GitHub or GitLab, and there are native products available from cloud providers as well. And just a small note here, AWS has discontinued its source control service, which was AWS code commit, so you will have to go elsewhere. If you are on AWS, you can be using something like GitLab, Bitbucket, or GitHub. And what will be the branching policy? Who all will be the collaborators? So all these things are done in the design phase itself. And then the next phase is development. Now, development is the phase where the actual work starts. First is branching strategy and code review. So whenever developers are writing the code, they will be writing in their local machines, and then they will be pushing the changes to your central repository. Second is local builds and unit tests. So developers will be performing local builds and unit tests. What are unit tests? We will see them in a little while. Shift left security. Now firstly, let's understand what is shift left. Now previously what used to happen was the security was only dealt with when we were deploying the application or when the application was completely deployed. But now we are adhering to the shift left approach. Why we are saying it shift left? Because if you go from 1 to 8, you are going left to right. Previously it was security was applied here or here, but now we are saying shift left. From the requirement gathering phase itself, start thinking about testing, security, and automation. Hence, even when the developers are developing, SAST and SCA are still performed. What is SAST? SAST is static application security testing, and SCA is software composition analysis. Now when the code is being written, the code is static, and that is why static testing is performed. When the application is in running state, then we perform something called DAST. DAST is dynamic application security testing. So static scanning when the code is being written, so developers are in their IDEs, and these static testing tools are integrated within the IDE, and then when the application is running, you have something called DAST, and we'll be seeing that shortly. Now there are tools that are popular. So if you want to perform static testing, then you have SonarQube, which can test your code. You have check marks. For DAST, you have OWASP, ZAP, and there are plenty of tools that are available at your disposal. Then the last point is pre-commit hooks and feature flags. Now what are pre-commit hooks? Pre-commit hooks are local guardrails that enforces code quality security even before the code is pushed to your GitHub repository or to your choice of source control. Now let's talk about the fourth phase, that is the build phase. Now I want you to understand that when I talk about build and deployment phase, these are of paramount importance when you are releasing a new version of an application or when you are deploying the application for the very first time. So In this section, we will briefly talk about the build stage, and then we will zoom in into this as we progress with this lecture. Now, first point is compile and package code. So whenever you have a source code, it is in raw format. You must compile it and then package it. And once you do this packaging, you receive something called an artifact. So whenever you are packaging a software, then the output that you receive is called an artifact. See, do not limit your imagination here. So whenever you are building something, whatever the result of that is known as an artifact. So even if you are building a container image, the container image that you receive is also an artifact. So whatever is the result of that build stage produces some output, and that output is called artifact. Second is reproducible build pipelines. Now, if you have a stringent process for build, then whatever your artifact is in your local machine, the artifact will work fine in your production pipelines as well, in your development pipelines as well. For example, if I'm creating a container image and I run that container image onto my laptop that has Docker engine, it will work, and any machine that has Docker engine installed all over the internet, that container image will behave the same way in that machine, because the underlying Docker engine was the only requirement for that container image to run as a container anywhere. Similarly, if your artifact is received in one machine, that artifact should be reproducible. So whatever results that you see in your local machine, you should also see those results in your production and dev pipelines. Here, that is what we mean by reproducible build pipelines. Next point is artifact registry storage. So whatever your output you receive from the build phase, that output should be stored in some sort of registry. So when I talk about container images, you have different image registries that are available that you can use to store your images. You can use Docker Hub, you can use AWS's Elastic Container Registry, and so on. When I talk about application artifacts, so application artifacts are predominantly the artifacts that you receive post building applications source code, and that output can be stored also in a registry. Now there are different sort of registries for them. For example, you can use Nexus or JFrog registries to save your artifacts, or you can also use native tooling that is made available by the cloud provider. Next point is supply chain security. In parentheses you see SBOMs, and SBOMs means software bill of materials. Now software bill of materials, they comprise of everything that is used to build a software. It could be your image, it could be your application, it could be your artifact, etc, etc. So essentially this line implies all the supply chain must be secure. So if there is code, you should be using SAST and DAST. If there is container, you should be using static and dynamic scanning. So what is static and dynamic scanning when I talk about containers? So if your container image is there in a registry, then your container image must be scanned. If you have a running instance of that container image, that is if you have running containers, then you should be scanning your containers as well, and this is also called runtime scanning. So if I am talking about your containerized workloads, there should be a two-step scanning mechanism. First, scanning should happen for your container images. Second, the scanning should also happen for your running containers, and there are multiple tools available for this. I will let you explore Trivi, Anchor, Sneak, and so on. Then the next phase is testing phase, and in parentheses you see continuous. Now testing is also adhering to shift left approach when we are talking about modern SDLC. So right from the development phase, the testing is ongoing, which is why you see in the second point we have unit tests mentioned here. Now let's understand what testing means and what are different types of testing that you will see in your day-to-day work. Now testing in general implies testing something whether it is working as expected or not. That is testing. So for example, if I want to test whether my connection to the internet is working or not, I'll try to ping google.com, and if it works, I'll know that my connection to the internet works. Now let's see what testing means when we talk about a software. First is unit and integration test, and I want you to take example of the same banking application that we have been talking about. So unit testing is my banking application could have several functionalities. It could be used to check your account balance, it could be used to check your passbook, it could be used to apply for loan, and so on. So this application can be divided into different units, and that is what unit testing means. Unit testing means testing different units of your application. So if I want to test, let's say, account statement, I will see whether the user will be able to log in and check its account statement. So that is called unit testing. Now what is integration testing? Integration testing is how your application behaves when 2 or 3 components come together. So if I want to check my account balance along with my passbook, then these 2 components of the application must work together. Hence, when you are testing multiple components of an application, it is called integration testing. Essentially, how the application behaves when multiple components come together. Second is performance and load tests. Performance implies how the application is behaving, what are the metrics, what is the speed at which the requests are catered, and load tests are how my application is behaving when there is, let's say, 90% load on my application. Then in testing itself, you have security scans, you have SAST and DAST. You see, there is no stage or phase named security because security must be in mind from point 1 through point 8. So you should be taking care of security, testing, and automation in all the stages of your SDLC. So security scans we have already discussed, SAST and DAST. Then there is pen testing. Pen testing is penetration testing, and this testing is typically performed once in 3 months or once in 6 months or once in a year. Pen testing involves knowing how the application will behave when there is an attack, for example. Then the last one is smoke and regression suites. Now smoke testing is a quick testing. So if, let's say, you released an application, you quickly see whether the application is accessible or not. This is a simple smoke testing. Regression testing is you test the application thoroughly, whether all the functions that my application was supposed to perform are being performed by the application or not. So regression is a thorough testing. Now let's move to deployment. Now in deployment, we know how the deployment should be. You first will be deploying into dev stage, and then that will be graduated to staging, and then that will be graduated to prod stage. And we will be discussing this in greater detail as we progress with this course. Second is progressive delivery strategies. There are multiple delivery strategies like blue, green, canary. What you use depends on what strategy was finalized in your design stage. Now next is infrastructure as code. So you should be using tools like Terraform, Helm, Ansible to do the deployment and configuration. The next is rollback and roll forward playbooks. Rollback is how you will roll back the application. You should have strategies in place. Roll forward is if, let's say, you have deployed the application and you can correct the error quickly, how should you be doing that? That is called roll forward. Then next is operate and maintain, and this is the operations phase of the application. So here you will be dealing with monitoring and alerting. So you should have an observability posture that will ensure you can operate and maintain the application properly, and you will be patching the resources, upgrading the resources. You will be taking care of the DR in case something fails. You will be restoring it from the backup. Incident response and scaling, all these things will happen in the operations phase. And the last one is feedback and improve. I want you to know that this is a critical phase. This is where you collect the mistakes that you have made over the past. You make a collection of that, and then you also take feedback from the users. Users will be telling you what features do they want, what else would they like to see in the application, what are the problems that you are facing. And then you, as well as DevOps folks, would have proper observability posture to know what all are the metrics that were not behaving properly. So you will take that into account. You will be discussing those things with your development teams, and all these things will be jotted down in feedback and improvement section. And once you have done that, then you will again move to the requirement gathering phase. You will collect whatever you have gathered, you will again design, and this process will go on. No application is perfect. This process continues till the application is alive. That is what modern application development looks like. Now, before we move ahead, I quickly want to discuss waterfall model and the agile model. So when it came to waterfall, it was sequential phases, feedbacks came late, risky big bang releases. So what used to happen was, a work was given to a software development team. They would continue working for 4 months, 6 months, over a year, and then they will go to their client to show them what they have built. And the client most times would have said, I didn't ask for this sort of application, you have not done it right. Then the entire process had to be repeated. So this resulted in risky releases, and this was not acceptable. So that is where agile and DevOps come into picture. In DevOps, you make small frequent updates with rapid feedback, hence the deployments are safer. You discuss with your clients that this is what we are going to do, and then you deploy it. If you take example of big e-commerce website like amazon.com, they would be pushing hundreds of changes per day. And why they can do that? They can do that because first, they are using the agile and DevOps model for SDLC. So what I'll do is, I'll take you to the GitHub repository of this course, and here I am. I'll go to Jenkins basics to production. I will go to day 1 here, and in day 1 I want to discuss waterfall versus agile, and here you can see the differences clearly. Delivery, big bang release at the end, small frequent incremental releases when we talk about agile DevOps. Feedback comes late, feedback is continuous here. Flexibility is rigid, hard to adapt once requirements set. This one is adaptive. Risk is higher, issues found late are costly. In the agile and DevOps methodology, we say fail fast in development, so that we know this code or this application is not working as expected. You fix those changes, you again deploy until you fix the problem permanently. So that is how agile and DevOps work. Team collaboration, siloed. This is cross functional. So dev, QA, and operations all work together. Examples: year-long banking system projects, agile DevOps, Netflix, Amazon deploying updates daily. I hope this section is clear to you. Now let's move on to next section, that is programming languages. Now firstly, I want to take a moment to explain you why I want you to know these things. See, you as DevOps and SRE engineers will be working with applications all the time. You will be deploying them, you will be rolling back, and so on. Hence, you must understand what programming languages are used when we talk about applications, and how these programming languages are segregated. And I will tell you, if you do not understand this, you will not be able to understand automation tools that are used in the build phase of SDLC, and the ownership of build phase is with DevOps folks. So let's understand programming languages. When I talk about programming languages, they can be categorized into two: compiled and interpreted. Now let's discuss compiled languages first. Translated before execution to machine code or to bytecode. So if I talk about compiled languages, let's understand what these are. Compiled languages requires some sort of compilation. Now what that compilation will do is it will take the source code and it will convert that source code into a non-human readable format. Now that non-human readable format could be machine code or it could be bytecode. So if I talk about C, C++ and Go, they use machine code. If I talk about Java and C#, they use bytecode. So when I talk about machine code, they do not require any runtime. What is runtime? I'll come to it. But when I talk about bytecode, a runtime is required. For example, if you have a Java application, then you would need JVM for that Java application to work properly, which is why you would have seen that if you install anything that requires Java underneath, you first must install the Java runtime, which is JVM. Now, before I start explaining this, let's understand these terms. What are these? First is artifact. Like I told you before, artifact can be thought of as a build output. Now that build output can be .jar. When I talk about Java, it can be .var. .var is also associated with Java. It can be .exe or it could also be a Go binary. Now what are runtimes and interpreters? These are execution engines. Example, JVM, .NET CLR, Python, Node.js. No, Python and Node.js are interpreted languages, but I will explain a small thing right here. So when I deploy a Java application, then I require a JVM runtime. And if I am running a Python application, then I will need a Python interpreter. Similarly, if I'm running a Node.js application, I would require a Node.js interpreter. Now we will discuss this deeply in a later section, but for now I just want you to have a basic understanding. Then there is middleware for extra app services. Now there are specific formats that are related to Java that are .var and .ear. .ear you don't see here, but we'll discuss that in a little while. Now they require special app services. Now these apps could be Tomcat, JBoss or WebLogic. Now what exactly is middleware? Middleware is a layer of software that sits between the application code and the runtime, and we will see this in a little while. Then at the very last, it is dependencies. Now dependency could be any dependency. If I am having an application, my application could be dependent on a configuration file. It could be dependent on a specific version of something. Hence, anything on which my application depends on can be thought of as dependencies. What I want to do is I will take some time to specially discuss Java. And why I am doing that? Because Java and Python are the most popular programming languages that you as DevOps folks will be dealing with. So if I move to the right of the screen, then the artifact format for Java could be .jar, .var and .ear. Now, firstly, needs runtime. All of these require JVM runtime, but only .var and .ear require a middleware. Mostly you will see .jar, so you will not be deploying a middleware. But in case your application requires Tomcat, JBoss or WebLogic, then you would be generating artifacts in .var and .ear format. Jar is simple Java archive, var is web application archive, EAR is Enterprise Archive, and as the name implies, this is used in enterprise grade environments, and you can read the GitHub notes if you want to know more about this. But for now, I will leave this here because this is the high level information that you need. The key point here is when you are talking about jar, you don't need a middleware, but with .war and .ear you need a middleware. But JVM is required in all these three formats. Now, requires build stage, and in parentheses you see compiler plus tools. Now, when I talk about compiled languages, as the name implies, compiled languages, they require a compiler. That is what we understand. So compiler will convert the source code into non-human readable code, which is machine code or bytecode. And machine code is for these languages, bytecode is for Java and C#. Now I will move to the left of my screen. So there are different compilers for different compiled languages. For Java, the compiler is called JavaC. For C, it is GCC Clang, C++ this, Go this. There are build tools at your disposal. Now we will see why these build tools are needed later, but for now I want you to understand that build tools do not just invoke compilers, they handle dependencies, packaging, tests, and artifact publishing. See, if you have written your source code in Java, then there could be multiple dependencies that must be handled for your source code. If you are on Mac, you have Homebrew, which is a package manager for your Mac. Similarly, these build tools act as package managers and they resolve the dependencies that are there in your code. For example, Maven is a popular build tool for Java, and this build tool will not just invoke the compiler, it will handle the dependencies, packaging, testing, and even artifact publishing. And we understand that artifact is the result of a build output. So Maven and Gradle are popular build tools, and we understand this artifact format could be .jar, .var, and .ear. .class is not widely used. It is a very niche use case. Then there is C, and you can read about what are the compilers and what are the common build tools. But here I am telling you that when I talk about build tools are not just for compilation. They can do a lot more than compiling a compiled language. Now let's move to the right of the screen to see other points. Faster execution, CPU direct. Now why there is faster execution? This machine code, that is non-human readable or bytecode, can be easily understood by the CPU. But just a caveat here, bytecode runs on a runtime like JVM, so there is some sort of translation that this JVM does before sending the inputs to the CPU. But at large, compiled languages are faster than interpreted languages. Now portability. If I talk about containerized, we know that containerization in general is best for portability because you package everything that the application needs in the container image, and wherever that container image runs, your software will run there. But when it comes to non-containerized, these artifacts are specific to OS and CPU, plus they need correct runtime. And if there is a mismatch between these, then the software will not run properly. And this is understood. So if, for example, a Java application is designed for Mac and I try to run it on Windows, it will not work. So it is OS and CPU dependent, plus needs correct runtime. What if I am trying to run an application in a machine that does not have JVM? It will not work there, or maybe it needs a specific version of JVM, then also it will not work. Now the key point is code is hidden. So as we understand that these tools, the build automation tools like Maven for Java, will convert the source code into bytecode, and if it does that, then that code cannot be read by humans because it is binary only. Now examples of compiled languages are Java, C, C++, Go, Rust, and there are plenty more. Now let's discuss interpreted languages executed by interpreter at runtime. So understand, previously when we were discussing compiled, the source code was compiled into a non-human readable format, but here these are not compiled prior. What happens is you write the code and then there is a interpreter that does the execution line by line. So there is no explicit build step here. Previously there was a build step, which is why we had automation tool come into picture and do the build for us. In interpreted, there is no build step and the execution is line by line by the interpreter. Portability, containerized workload, of course they are portable, but non-containerized workloads, for example, if you are trying to run a Python application in your laptop, then your laptop must first have a Python interpreter and all the dependencies must also be met. So for example, if your application requires Flask framework of Python, then that must be installed. Version mismatch, and if you already have Flask, maybe you do not have the version that is needed by my application, so the version mismatch risk is always there. Now this is an important point, code visible. So if you have a Python application, when you share that application with your user, then the code is visible to them. Examples of interpreted languages are Python, Node.js, Ruby. Now let's move to the next section. See, I want you to know that you as DevOps engineers will not just be deploying resources onto containerized workloads. You will also be deploying resources or your applications onto non-containerized workloads. Now in this section, I want to give you a flavor of how compiled and interpreted languages will behave in both of these environments, and I am telling this specifically from the point of view of the build step. Let's scroll down. First, let's see what happens to the containerized world, and we are talking about compiled languages first. And we know compiled languages, there is a build step where you do the compilation. And what is compilation? Changing the source code into a non-human readable format. So first you see source code, then here you have tools like Maven, Gradle, Make for different programming languages. Maven and Gradle are predominantly used for Java. So let's say our source code is in Java. Here we have Maven. Maven did all the things for us. So Maven handled the dependencies, packaging, testing, and then finally artifact publishing. That is what you see here. Then the artifact was generated, and let's say the artifact was generated in .jar format. What is the next step? We are talking about containerized workloads. So when we talk about containerized workloads, in the next step we'll be creating a Docker file. Now here is the Docker file. What I'm saying in this Docker file is from OpenJDK. Why I am mentioning OpenJDK? Because understand, for this .jar to run, I need the JVM runtime, and OpenJDK is the base image that has that JVM runtime available, which is required by my .jar file. And in this step I am copying the app.jar file, and here in step 2 I am building the container image. And once the container image is built using this Docker file, we can finally deploy it as container. Now I want you to clearly know that when I'm talking about containerized workloads, it is a two-step build. First I am building the code, and then I am building an image. So here, when Maven was used to publish this artifact, I copied this artifact in my Docker file, and then an image was created which had this artifact. Now let's see how non-containerized workloads behaves when we talk about compiled languages. Here everything remains the same. It is just we do not have a Docker file. We are deploying onto a VM, but this VM must have everything that this needs. Now what do we need? Firstly, we need a runtime. If we are deploying a Java application, we need a JVM runtime. Then second is middleware. Now if we were receiving the output in .war format, then we would also require a middleware, and that middleware could be your Tomcat or JBoss. Now that we have this understanding, let's see how interpreted languages will behave like Python. So if I move here, I have containerized workloads, and here I have interpreted languages. See, the source code is this, and I'm directly moving to the creation of Docker file. There is no build step that involves compilation or packaging. What I am doing is I am saying this Docker file from Python 3.11. Here, why I am using the base image of Python? Because I know for my Python application to run, it requires an interpreter. And why is interpreter required? So if I move here, we learned here that when I talk about interpreted languages, they require an interpreter at runtime. That is why if you want to run any Python based application in your laptop must have a Python interpreter. So I'm saying from this, and this image will have the Python interpreter. I'm saying copy source, so I'm copying the source code into my Docker file, and the resultant container image will have this source code. And here I'm installing the dependencies. I'm saying pip install -r requirements.txt, and this file will essentially have all the packages that I use, and pip is the package manager for Python which will install all the dependencies, and I'll have my image built here, and then I can deploy. Now let's contrast this with how non-containerized workloads will behave. So here I have the source code. Now the source code could be in any interpreted language. Here it is, let's say .py for Python. Now we deploy it onto the VM, and here are the must have. Interpreter must be there. So this VM must have Python. Dependencies should have been installed using pip, npm or gem. Pip is for Python, npm is for Node.js, and gem is for Ruby. Last one is isolation. Now this is an important piece. Okay, venv is virtual environment for Python, nvm is node version manager, rbenv is a Ruby environment. I want you to know that there could be multiple applications deployed onto your VM. One application might require a specific version of Python, another application might require a different version of Python. In that scenario, for Python you can use virtual environment. Now what this will do is this will allow you to have different versions of Python for different applications, and similarly you can do this for Node.js and Ruby as well. I hope you have understood this. Now before I let you go, I want you to know one more thing. You understand that the build process is automated, and build process is automated using automation tools like Maven, Gradle, or for C you have make, CMake, and so on. So what if these build automation tools were not there? So for compilation it is fine, you could have done the compilation, but what about dependencies, what about packaging, what about tests, what about artifact publishing? This would have been a chore for you. So if I move to my GitHub repository, what I have done is I have one section where I am defining why build automation matters, and it is there because you don't have to have that classic problem works on my machine. So whatever artifact you generate are reproducible, traceable, and environment agnostic whenever you are using build automation. So you want whatever artifacts are generated should work the same way in dev, staging, and prod, and this has version logged as well. So results are predictable and safe to promote. Now, before I let you go, I want you to know one thing. We have discussed SDLC, and these are the phases of SDLC that we discussed. I want you to understand that there must be some tool which could help us with these all things. What is that tool? And the tool that will help us with all these things are CI/CD tools, and in the next lecture we will explore this in a detailed way. So for now, that's a wrap for day one of our Jenkins Basics to Production series. Today we laid the foundation by breaking down SDLC phases, contrasting Waterfall with Agile, exploring compiled versus interpreted languages, and understanding artifacts, runtime, dependencies, and build processes. In the next lecture, we will zoom into continuous integration, testing, delivery, and deployment, and then start connecting the dots on why Jenkins is such a popular choice for automation. If you have any questions, feel free to ask in the comment section and I will reply. If this helped, do consider liking, sharing, and subscribing. It will mean a lot to me. Thank you very much.